do it.
So, good morning. Let me go over certain dates and I'll definitely take questions when I'm done talking about this. So please hold off for a few minutes, okay? So as you know, the last lecture period is on December 5th, on which day we will have our exam 3, which will cover modules 5 and 6, which is ordinary differential equations and statistics, okay? Today and Thursday, I'll try to wrap up statistics. And later, that is right after class today, I'll be posting homework 6, which will be really short, just 3 problems based on whatever we have been discussing last lecture and today. And with regards to holding more optional recitation sessions, which I'll record through Zoom and post it, I wanted to do one yesterday, but I wasn't available. I'm still thinking about doing one on 29th, December 1st and December 4th, which are not really our scheduled days. I will be recording these. So what I am trying to gather is, would these times work for the majority of you? For others who could not come, you can still watch the recording. So on Wednesday, I'm thinking 11 a.m. to noon. On December 1st, I'm thinking 9 to 10 a.m. And December 4th, I'm thinking again 11 a.m. to noon. These are all through Zoom. You don't have to go anywhere. Just sign into your computer. Would this time work for how many of you can make it this time? Okay. If I made this say noon to 1 p.m., would that make it better for?
Yeah.
Show of hands, please. Noon to 1. So that seems like more people can join. So noon to 1 p.m. tomorrow. Okay. On Friday, this is really the only time that I can make work in my schedule. Would that work? How many of you can actually attend in the morning? 9 to 10.
Maybe.
We have class. Okay, but anyway, there's no option there. So I have to do it at 9 to 10 if I want to do it. Monday, 11 a.m. to noon. I assume the same people can attend, but other group will have a problem. How about if we make it earlier or later, like 10 to 11 or noon to 1? Noon to 1. If I say noon to 1, how many of you can come? That is those who want to come. All right, let's do noon to 1 p.m. So what I'll do is I'll send Outlook invites with the Zoom link for all 3 days that you can accept and use to join. Okay. I said homework 6 will be posted shortly after class today. It's due on 5th, right when you come for the exam. Just bring your submission. The class participation exercise for module 6 will be done on Thursday. It's going to be like a short problem solving exercise. Since it's near the end of the term, I just wanted to give you a heads up so more of you will show up. Okay, so don't lose that 1% by not showing up on Thursday. And the general plan is all the scores will be posted by the end of day on study day, which is December 7th. Homework 3, 4, and 5. Homework 3 and 4, we hope to return it this Thursday. Exam 2, I hope to return it this Thursday because I'm grading it. Homework 5, 6, and exam 3, we'll grade it next week before evening on Thursday. Okay, so that hopefully by around 5 p.m. on study day, you can make the choice whether or not you want to take the optional final. Okay. The optional final is comprehensive. Let me write those details down. Optional final. It is what 60%. It is comprehensive, meaning it will cover all. Comprehensive. It covers all 6 modules. Same level of difficulty as you saw in as exams 1, 2, and 3. Okay, it will have no more than 6 problems. I say no more because in the exams, I had like 4 problems, 2 for each topic. What I will do is in the comprehensive exam, I might combine a certain number of topics and test 2 topics through the same problem. So on the exam, you might be having only 5 or 4 even, but definitely no more than 6, even if I decide to test all 6 topics through each problem of their own. Okay, so hope that makes sense. It will, of course, be 120 minutes. So that's about 20 minutes per problem. Same average. In the exams, we had 4 problems, 80 minutes. Now we have 6 problems, 120 minutes. I said wait till the end. This exam is worth 60%. So how that works is your scores on exams 1, 2, and 3 combined. If it is great, if your performance on this final is greater than your exams 1, 2, and 3 scores combined, we'll take the exam. Unfortunately, if you attempted the exam and you still could not do better than your exams 1, 2, and 3, we will still take that score. Whatever gives you an advantage in terms of your grade. Okay. So since we are anyway preparing it and there is a centrally scheduled slot and we are doing the work of thinking about the problems, I would encourage all of you to take it to maximize your score and chance for a better grade, especially if your letter grade in the midterm, that is the midterm grade is anything not a B plus, I would strongly suggest you take it. That's just some advice I'm giving you. Okay. Now I can take questions. What is your question?
Are we going to be able to use our computers and a Word and a sheet of paper with like notes on it?
Most likely you will either have like 2 sheets of notes, at least 2 sheets of notes, or open book and notes. Okay. I still haven't decided if I'm going to have like the computer given to you and ask you to do Excel calculations, or just keep it close to the basics, pencil and paper plus calculator type stuff. So I still haven't decided about that. But once I decide, I'll tell you through email. Okay. But you'll have at least access to notes, 2 sheets of notes.
What about exam 3?
Exam 3 also you'll have 1 sheet of notes. That is, you can either bring either 1 sheet of notes, or it could be like exam 2, open book notes plus computer. It really, once I figure out what is that I want to ask in the exam, only then I can decide what is appropriate that I can allow. So by end of this week, I'll send out through email definitively 1 or 2. Yes, I'll come to you. Yeah.
Will exam 3 basically be like what we did last class and the next 2 classes with the statistic plus like the
Or, yeah, exactly. Yeah. That's why I want to use these sessions to solve some examples to get you better prepared.
If we did good on exam 1 and bad on exam 2.
No splitting. As restaurant people would say, no substitutions. Okay. You either take the comprehensive final or you don't. That's it. Yes.
I was just gonna say, why are you recommending if it's like a B average to take for them?
Well,
students that want to get an A, or are you saying that you don't know if there'd be enough?
no, the different people take up the final for different reasons. Somebody wants to jump from a C plus to a B grade, they should definitely take it. Somebody is on a A minus, they can still take it and aim to do better to jump to a A. So everybody has their need to take this. So if you feel that it is worth your time and you have a realistic chance based on what your score is at the end of study day, you should take it. Finally, it's your decision.
Did you say that the Zoom presentation sessions will be recorded, so if we can't go to it?
Definitely.
Okay.
If to provide equal access to everyone, it will be recorded. There will be no, like, I won't be teaching new concepts. I will be just doing examples. I will post it promptly right after the session is done, so that anyone can watch it, and after watching it, if you have questions, even though I don't set aside a time during this time, this week, next week, until your exam, I will try to prioritize, and whoever wants to talk to me, I'll either meet with you in person or through Zoom. I'll meet with you. I make that promise. Yes,
So when you say open book, open computer, you're not gonna like give us any table, like.
yeah, if it is, yeah, I mean, in any case, I'm not going to tell you what to bring. You know the list of topics, you prepare it and bring, that's it. I won't restrict, I won't tell you to bring this or that.
Like when we print things out and
You what?
when we print things out and.
Yeah. I mean, I'm not going to come and check what you bring, so. Yeah,
When is that exam? Is that the 14th at Thursday?
I have to look in the central schedule to see when our course is assigned a slot. We are 11:20 AM slot, so I have to look, I really don't have an idea now.
It should be Thursday.
The 14th?
Thursday, okay, yeah.
So for exam 3, will you give us a T table or do you expect us to bring that?
I'll give you any information that you need. I won't tell you any formulas, but if you need T tables or normal distribution tables, I'll provide. It'll be provided along with the questions. Any other questions? So the thing that we have been somewhat struggling is the grading. We really wanted to hand back both the homework and exam scores today, but we'll definitely try to do it on Thursday, so that you will have all your scores for the entire course. That is, if you decide not to take the final, at the end of study day, you should approximately know your course total. And the letter grade scheme, I won't release it until after the final, but at least the midterm splits are indicative of where you are going to land. It probably will be a little tighter than the midterm grades, but at least it should give you a picture that you're likely to. Anything else that you would like me to try or provide in terms of help that can help you score better? I won't curve the class, that much I'll tell you. Your success is not at the expense of your friend's failure. So it's not like the bottom 10% is going to get a C minus, it's not that way. I usually try to use absolute grading to come up with a cutoff that I think is indicative of good performance or mediocre performance or bad performance in the exercises and exams that I set. So it will be letter grading with absolute cutoffs. Okay, that much I'll tell you.
You said that will be released after the final or after?
It will be released, yeah, it will be that is after the everything is done and I have the complete scores, finalized scores for the entire class. I will try to sit and come up with the cutoffs based on the performance and the difficulty. And when I email you one last time for this semester saying everything has been posted, I will post that cutoff scheme in that email for you to make sure that, oh, I got a 91, I must be A minus or A or something.
Well, we have a general idea of what the scheme will be, grading scheme by the study day, do we know where we stand? Because I'm assuming you're gonna modify it based on the final scores, but is it gonna follow kind of the? letter scheme?
Loosely follow the midterms here,
Okay,
if I go any finer, I'm kind of constraining myself too much. If I tell you any more detail now, then I can't make any adjustments, so I'm not going to.
so will we be getting a letter grade for the study day?
No, what I'm saying is, you can take your course total And you can take the letter grading scheme I used for the midterm grades and use it as an indication.
Okay.
If I tell any further, then there is no elbow room for me. That's why I'm not saying anything. All right, so can we move on to the topic of the day? Are we done with questions here? Everyone's clear how you will decide that whether you need the final or not? Okay. If you already have, say, combined 1, 2, 3, if your score is already above 55, as a student, I wouldn't see much gain in taking this because the comprehensive final is a little more stressful than your exam. It's 6 problems, 2 hours. It will try to couple topics, like it might draw a concept from module 1 and a concept from module 3 and try to ask you a problem that is kind of integrated. So it might be difficult to better your score. If you're already at 59, I don't see how you would better your score. But if you are at 45, anything below 50, I strongly recommend you take it. So can we move on? Yes. Okay. So last lecture we talked about reliability estimates of the mean. That is, if you have a set of observations, say x1, x2, x3, up to xn. You know what the mean is. You've all encountered that many times over the last few years. It's the sum of all the numbers divided by the number of observations. And standard deviation. I call this sigma x equal to 1 over n minus 1 summation I equal to 1 to n xi minus x bar whole square, and the whole thing under a square. So even though it was sort of a lengthy discussion, what we saw the other day is the standard deviation sigma x is inherent to the system being observed. That is, sigma x as a fraction or percentage of the mean is not under the observer's control. So sigma x, that is the standard deviation itself, cannot be used as a measure of how reliable the mean is. It doesn't tell us whether the number of observations is sufficient enough to draw any conclusion about the quantity you are measuring. It could be a voltage, it could be a survey, it could be height, it could be length, it could be any quantity. So what we saw is that we defined the standard error estimate, which is T of P comma nu multiplied by sigma x divided by square root of n. Properties of the standard error estimate are obvious. It scales with the standard deviation. So the error is higher if you have higher standard deviation. It also scales inversely with the number of observations to the square root, which means the standard error estimate goes to 0 as you make the number of observations large. And the parameter T of P comma nu is called the students T statistic. Okay, so P is the level of confidence that we are looking for, typically 95%. Typically 95%, and mu is called the degrees of freedom, which is number of observations minus 1. Just summarizing all of last lecture, so that before we move on, you'll have an idea. So if you have your observations to be something, you have x3, x4, x5, 6, 7, 8. You can calculate their average. Let's say the average falls here. This is x bar. X bar. We write x lies between x bar plus minus T statistic multiplied by sigma x divided by square root of n with 95% confidence. This is the statement in symbolic form, and I also said this has to be read as the true value of x. The true value of x lies between x bar minus T sigma x divided by square root of n and x bar plus T sigma x divided by square root of n with 95% confidence or probability. This is the literal translation of this sentence. So either on Thursday or on the exam or on the exams 3 or final, you could get like a very short question asking you to provide this range and also write in simple words what does that represent. So you are expected to understand that if you think about, say, x bar, and this is x bar plus ci, and this is x bar minus ci, where ci is t multiplied by sigma x divided by square root of n. The true value is likely to be found in this range with a certain chance, and that chance we estimate it as 95%. So if you wanted 99%, that range will be even wider. 99%, 95%. If you want it with only 50% reliability, it will be even narrower. So that's what this T statistic takes care of. Varies with the probability or confidence. This is the summary of last lecture. And we did, I think, one example related to that. So before we move on, I'll do one more example. Anything that is not clear from last lecture, you want to ask again, even if I said it multiple times, don't feel shy, just ask. Something you want me to repeat.
So last lecture you were talking about how the way to like decrease your standard error would be to change your interval, like or your number of observations.
Correct.
And that's also going to affect your T.
Correct.
Okay.
That T depends on the probability level, confidence level that you're looking for, and the number of observations you make. And that observations, the more observations you make, the T statistic value itself plateaus off at some point, which we'll see in the table now. But the more important factor is the square root of n appearing here. You can easily understand that if you made, say, for example, 10,000 observations or 100,000 observations, this standard error estimate can be made as small as you want. So if you want the standard error estimate to be very small compared to your mean, you can always make more observations. But the soft aspect of that is, or logistical aspect of that is, making more observations in many experiments or projects come with a cost related to the overall project execution itself. So for a statistician, it's easy to say, go make 10,000 observations. But for the engineer, it's a complex decision. Yeah.
Where do you get the value for the this thing?
I'll tell you. It is in the handout that I posted. If you go to page 131, I think, or maybe not 131, 137. So to look up this T statistic, you need to look up page 137 in the handout. So that handout has been posted on the Canvas page, which you can download, and I'm going to bring it up on the screen now. So while I bring it up, I would ask you to just go turn the pages to last lecture and just look at the example we did, because we are going to do one more example like that before we move on to the next topic. So even though this topic that I presented to you actually assumes a lot of things. I assume that you know what is chance, what is probability, what are measures of probability like mean, average, standard deviation. I assume all of that. What I am trying to present to you is, as engineers, you would be using statistics most commonly in evaluating your measurements or observations. And I'm trying to provide you a way to understand that what you observe, which is the mean and standard deviation, is not directly the reality that you wish to. the mean and standard deviation have to be used combined with statistical concepts like the t-statistic, so that you can predict in the end the range in which the true value is likely to be found with some confidence, which is what goes into your calculations as part of a design procedure or some kind of a decision-making routine. So understand that we are kind of airdropping you into a very specific concept within statistic, and I'm teaching you how to do this calculation, how to look up this p-value, how to combine this and write this statement. I'm not teaching you very from the basics, which is by my intention, because this is what I think will be useful to you. If you take this class in another time with another instructor, they might give you a more basic treatment, try to come up with what are distributions, what are probabilities, what is a random variable, which I'm kind of skipping. Okay, maybe some of that I'll touch on Thursday, but I think this will be useful to you. Maybe years later you can tell me whether this is useful to you. All right, so we want to go to page 137. So to know the so to see this topic, described in words, you can go to this section. Oops, section 4.4 in the book. Okay, statistics of finite size data sets. That's what we have been discussing since last lecture. Okay, section 4.4. Section 4.4 is what you need to refer to, and page 137 is the table where you have the t-statistic. So if you see here, they start with mean, variance, standard deviation, degrees of freedom, and then they talk about the statement that I wrote. So see here, this is the important statement. This is the important statement. The interval plus or minus t multiplied by the standard deviation represents a precision interval given at a probability p% within which one should expect any measured value to fall. So all your observations, or at least 95% of your observations, will fall within this range. And that is why we say that this is the range most likely to contain the true value of the quantity that you're trying to measure. Okay. And then here is that table 4.4. Not 137, 131, table 4.4. So we saw this last lecture. The t-value is a parameter that appears in a statistical distribution called the student's t-distribution. It has values calculated at 50%, 90%, 95%, 99%. And this first column is the degrees of freedom from 1 to infinity. Two observations. If you move from left to right, as the probability increases, the t-value increases. So if you take any row, 694, 1.771, 2.160, 3.012, it increases across left to right. If you go from top to bottom, it also increases with the degrees of freedom. Sorry, it decreases with degrees of freedom, but its value flat lines. If you see here, for 10, it is 0.7. For 5, it is 0.74. For 20, from 0.7, it has dropped only to 0.687. And from 20 to 60, it has dropped only from 687 to 679. So the rate of drop is slowing down. For practically anything more than 60, it doesn't change and it's given constant values. So if your exam problem says there was 71 observations and you need to calculate the t-value at 95%, how will you use this table? Just use infinity value. In fact, if you are given, say, 47 observations, you are between 40 and 50, I wouldn't even bother doing linear interpolation. I would pick whichever is closer. So 47, 50 is closer, 40, 42, 40 is closer. So because the graph or the values change so much slowly. Okay. Before we do an example, any questions? No, shall we do one more example? I think we did this problem last time, 4.24.
Yes, we did it for N1, I think.
No, not 25. We did 24, 18 megapascal, 924 megapascal. I remember that. All right, let's do this problem. No, not this one, not this one. Standard deviation, maybe that's the. Have an example. All right, let's do this example 4.4. Consider the data of table 4.1, compute the sample statistics for this data, estimate the interval of values over which 95% of the measurements of X should be expected to lie, estimate the true value of X at 95% probability based on this finite data set. So table 4.1. Where's table 4.1? Yep, right here. So you have 20 observations and you have the value of X's from given to you like for each of the observations. And using this, we want to calculate the mean, which is easy, and the true value or the range in which the true value is expected to lie. Okay, just a simple application of this formula here. Like I did in my illustration, we have 20 observations. The only painful thing about this example is you actually punching this into your calculator to get the average. So you can do this somewhat easily, I think. If you look here, 1 seems to be a number that is somewhere in the middle. So I would rewrite everything as either less than 1 or more than 1. So this is minus 0.02, this is plus 0.07, minus 14, plus 16, and so on, so that it's easier to add up and get the average value. You see what I'm saying? So here are my 20 observations. First observation is negative 0.02 plus 0.07, negative 0.14 plus 0.16. Because I'm trying to simulate how I will do this in the exam to save a little time. Plus 0.34 plus 0.04 plus 0.21 plus or minus 0.14. What do I have here? So these two I can combine 0.02, 0.02. I have plus 21 minus 14. I can write this 0.07 plus 4 minus 4. This is plus 0.05. And then the other end, I have plus 0.02 plus 26 plus 2 minus 0.06 plus 0.11 minus 0.01 minus 0.22 plus 0.06 minus 0.04. So I have 2, 2, 4, 0, 6, 0, 6. I have 22, 11 and 1. 22 and 26 I can write plus 0.04. I have 0.10. So I have 7, 9, 16, 20, 30. So average value is 1 plus 0.30 divided by 20, which is how much?
One point one fifteen or 1.015.
Yeah, 1.015 is the average. And we also need to get the standard deviation. I guess it will be simpler if we do this on Excel. Yeah. Just skip the lazy work and do this. You have a value?
1.019 is your average.
I mean, what is the standard deviation? I mean, we need average and standard deviation. You're saying 0.19?
Standard deviation, I got how many decimals do you want?
3 or 4?
For 4 decimals, 0.1577.
0.1577.
Yep.
Is it really that high?
Yeah, it's not true enough by it.
So mean is 1.0190 and standard deviation is 1577. So the degrees of freedom, mu value is n minus 1, which in this case is 20 minus 1 or 19. And the probability level is 95%. So based on these two, can you look up the t statistic and write it down from the table? 4.4, page 131.
Professor,
Yeah.
from the right side, you're missing the 0.5 plus 0.08.
I'm missing a 0.08.
Yeah, in between the 2, 6 and the,
Did you skip the third number?
yeah. It should-
Oh, okay, so that's why. So this is correct?
Yeah, yeah.
1.0190. Okay, can you look up the t value? Because if there is a skill in this, it's looking up the t value. And
2.086.
yeah, just give me 1 second. Let me go to that page. All right. So we have 19 degrees of freedom, that's here. And we also want to look up 95%, so which is this 2.093. Okay. So for those who are trying, I'll give you a second to actually read up this or read this value. The problem that you will encounter in your exam or your homework essentially will require you to read the problem, compute these two measures, identify the key concept is here. You need to understand that degrees of freedom is one less than the observation, and then use it to read the table correctly. Okay, so practice that. So t value is 2.093. Okay, so the standard error estimate is P statistic multiplied by sigma x divided by square root of n, which in this case is going to be 2.093 multiplied by 0.1577 divided by 20 observations or square root of 20. So this is example 4.4 in the handout. N equals 20 observations for xi. X bar equal to 1.0190. Sigma x is 0.1577. Based on this, number of degrees of observation is n minus 1, which is 19. And we want to get t statistic value evaluated at 95% and mu equals 19, which is 2.093 from table 4.4, page 131. So based on these, the standard error estimate is here, I write it here. Standard error estimate is T statistic sigma x divided by square root of n, 2.093 divided by. So this is all in one place for you to review later. Can you tell me the value of that estimate?
0.0738.
0.07.
0738.
Thank you. The last step in this problem is writing the statement. It says the true value of x, we'll call it x prime, true value of x is likely to be found in the range or in the interval. What is x bar? X bar plus minus the standard error estimate with 95% confidence or probability. So in our case, that would be 1.090 plus 0.0738 and that is the interval in which you are likely to find the true value with 95% confidence. I'll repeat just one more time. If you wanted P to be equal to say either 99% or 50%, T value will be higher or lower according. That is, if you wanted more certainty, the interval will become wider, and if you are okay with lesser certainty, the interval will become narrower. Yeah.
Is standard error the same as CI?
Yes. I've also used the name CI or confidence interval for this. So towards the end of last lecture, I think Alex, you asked the question, what happens when the number of observations is large? The table doesn't have any increase for that, okay? So we are going to answer that now. So whatever we have seen so far is for observations which are limited in number, and I define limited as, I think I said this last time, anything less than 30 is considered small in statistics, and anything 30 or above is considered a large data set. It's a very arbitrary definition, but it seems to work. Okay, so n less than 30 is considered small or finite sized data sets. Anything greater than 30 is considered large or not really infinite, but it's practically infinite sized data sets. If you see this table 4.4, table 4.4 for the t statistic, indicates that t value does not change significantly for nu greater than 30. We saw that, okay? Now we are going to generalize how do we connect these two worlds of small data sets and large data sets, okay? When you make many observations, or when you think about quantities that you don't directly measure, but you have heard of it many times, or you have seen it measured many times, we commonly assume something about those data sets. Like for example, if you think about the height of people in this room, we don't have to do a measurement, but you all have some gut instinct about how many people will be very tall and very short, or how many people will be about the average. That instinct, even though we didn't give a name for it in many circumstances, is the Gaussian distribution or normal distribution. The Gaussian or normal distribution is generally used to describe how random variables or how quantities vary in a large population. And for understanding that sentence, you need to first tell me how many of us are here. I think this class is about 31, including me 32, and today we might have about 26, 27 people. That is 27 observations of height of individuals. What are the ways in which you can summarize this information? You tell me.
Would you take an average of the height?
Average standard deviation. It gets you two numbers, so 27 numbers are represented as two numbers. That leads to a lot of loss of information, because some of us are very tall, we sway the average too much in one direction. Some of us are very short, we do the same in the opposite direction. How do you get a representation of the distribution of people of different heights in different groupings? That's one example. The other example is the one we talked at the start of the class about your letter grade cutoffs. What is but a letter grade cutoff? What is it supposed to do? I get 32 scores. This one, I'll give you this one. 32 scores. I'm supposed to assign letter grades to that group of students. What is that process I'm really doing there? Yes.
You are attempting to cut the letter grades off in such a way that you'll have a proper distribution among each of the letter grades.
Can you tell me what a distribution means?
Having, as in the type of distribution, or just what?
You have to, if you are using the word distribution, can you explain it in simple words without using the word distribution itself?
The spread of grades across each category.
Okay, I'll take that because you're saying the same thing that I want to say in slightly different words. I'll take that first. I can come back. Yes.
I guess you could say another way to describe what you're doing with your grades is you're just trying to allow people to understand the content of the task, so that way they can do harder stuff. So
No, that's not what you're saying. Yeah.
you're creating subgroups of.
Okay. So you use the word subgroups. What did you use?
Categories.
Categories. Good. I think we are having an English class here. So we had two words now, categories, subgroups. Anyone else wants to say something else? Yeah.
You're compartmentalizing your data into smaller subgroups or categories that are in those categories, the data you're spreading in them is close to each other.
Right. That is, if I'm taking the heights example, say suppose the height range in this room is between 5 feet and 6 feet 2 inches. Okay, I'm just making it up. Maybe there is someone taller, I don't know. So I have 5 feet on one side, I have 6 feet 2 inches on the other side, and or maybe I'll keep it 4 inches so that it's easier for me to talk about. So I'll say 5 to 5'4" is one group, 5'4" to 5'8" is one group, and then 5'8" to 6 is the another group, and then 6 to 6'4" is another group. You use three words: compartment, subgroups, categories. Statisticians came up with one common word, which is, kind of universal. They call it bins. If you treat all of us, if you take our names, write them on a card, and I keep 4 bins, and you drop your card in the bin into which you belong, we would get a distribution of how many people are in each category or bin. And this type of a representation is different from calculating average and standard deviation. What does average and standard deviation do? It reduces the data from 28 observations to 2 numbers, but it suppresses so much of information. What can you do with an average? You don't know nothing about what it tells about how many people are between 5'4" and 5'8". It just tells you one number. Binning, on the other hand, tells you exactly how many people. So if I have 4 bins, okay, 1, 2, 3, 4, I have the bin width, which is the 5th number. So with only 5 numbers, I can represent the data that describes 28 people. Why stop at 28? It can represent hundreds of people with only few numbers. And what is the name for this type of representation? You know this. This type of a bin representation has a very specific name, which you might have seen and used. Maybe now you're not able to recall. Bell curve is the Gaussian distribution that is a specific distribution. This is for any distribution. Bar graph is also another name used for histograms. Histogram. And before I go on, did you want to say something? No, you. While I was talking about bin, I thought you put your hand. So binning is a very generic name. If you have a number of objects or observations or data, you can literally close your eyes and picture yourself dropping objects into each bin. This helps me understand and remember this for these many years. So binning is classifying objects based on some attribute. It could be height, it could be weight, it could be eye color, it could be hair color, it could be some attribute based on which you classify the objects, and then you create what is called a histogram. So how does the histogram actually look like? That is, if you represent it as data, how does your raw data look like? So I have, let's say, 28 students and including me, 29 people in this room, how will the data for height look like? I'll have H1, 5 feet 2 inches, H2, 5 feet 6 inches, H3, 5 feet 3 inches, H4, 5 feet 8 inches, whatever, it keeps on going. This is my raw data. Okay. How will my reduced data look like? Reduced data, that is, if I just compute a mean and a standard deviation, that is 2 numbers. You are with me so far? You can imagine a list of 28 numbers and then 2 numbers. Okay. How will my histogram look like? That is, if I am actually binning and I have counts of how many people fall in each range. Actually, just to give it some reality, if you all don't mind, can I ask you to raise your hands if you fall in any of these bins? You don't have to identify what is your height, you just have to raise your hands when I ask you to. So, anybody shorter than 5 here, so that I have to extend this? No, that can be very, I don't want to. Okay, raise your hands if your height is between 5 and 5'4". 5 and 5'4". Maybe I should, I'll have to revise this, but it's 5'4" and 5'8". 1, 2, 3, 4, 5, 6, 7. Anyone else? 7. So between 5'4" and 5'8", I have 7 folks. Between 5'8" and 6 feet, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 to 6, 4. 1, 2, 3, 4, 4. Anyone else? I missed? 4. So that's 23. So our attendance today is 23. Right? Hopefully, yeah. So this type of representation where I have a starting point, okay, I'll call this say H naught, and I have a bin width which is 4 inches. So I have a delta H which is 4 inches. So I have 2 numbers plus 3 numbers. So that's 5 numbers. 5 numbers to represent or to summarize 23 numbers. So how will this data look like? If you plot it, it's going to look like I have 5'4" to 5'8" to 6 to 6'4". Anyone taller than 6'4" that I missed? No. So I have 7, and then I have 12, and then I have 4. So this type of representation is what is called as a histogram. Okay. If you look at this histogram, it typically has a shape. And the Gaussian function that you're so programmed to think about, even though it is going to be a little counterintuitive when I say it, it's meant only for a large number of observations. We can't take this 23 observations, and whatever we try to do with the Gaussian distribution would not be correct because it would be very choppy or forcing it. If we had a class, let's say, that had 100 students, that statistic will even nicely fit with Gaussian distribution because the function almost becomes semi-continuous because of the large number of observations. That's why when I think about your grades, I don't want to do curving the class, which typically makes or forces the instructor to take an average and set average plus 1 standard deviation is B plus, or A minus and so on. Even students who are supposed to have gotten a better or worse grades will be forced to take up grades that they don't deserve either way. Okay, so we don't want to do that. So this is general, that is raw data as collected always looks like this. It could be voltage, it could be height, it could be length, it could be anything. You get reduced data, which is average and standard deviation, which are easy to compute, you can easily automate. A histogram starts, it's initiated with the act of binning. Now, can you tell me in simple words what binning means, or how will you define binning? Yeah.
Visual representation of a range,
No, I want you to define the act of binning, literally,
throwing something in a bin,
based on
similar characteristics.
similar, based on some attribute. If you had a bag full of red, blue, and green balls, and you had 3 bins, you literally will take one, examine the color, and drop it in its bin. Remember this process. That is essentially what you do, whether you are handling data that pertains to any physical quantity. Literally, it is taking that quantity, examining its value, and placing it in one bin or the other. And the reason I asked you to show of hands is now you yourself, you binned yourself by raising your hand when your number was called. That is literally the process you have to keep thinking. Okay, it's about remembering how to think of this concept. Okay. All right. So you did the binning. You get a histogram, which is typically a range and n. So this range and then number per range. Number per range. Okay. So the concept here is the shape of the histogram. The shape of the histogram is what we call the distribution. The words have meaning. That is, when we say, suppose I have a class with 32 students, and there is about 15 students who are getting a C minus, and then there are 17 students who are all getting A minus or A. That is the class grade distribution, say between 65 or between 70 and 80, I have 15 students. And then between 90 and 100, I have 17 students. You all, most of you, I mean, you're all speakers of English. So what adjective would you use to describe this population? Yes.
Distorted.
Distorted is one. There is a more specific adjective we can find. Skewed. So let me write those. Distorted. Skewed. What else? Split. I heard it. Bimodal. Split. Bimodal. Bimodal meaning there are two kinds of people essentially. The entire there is not like a continuous types of people. There is just 2 types of people. Either they're doing badly or doing well. That's it. Okay. Sorry.
I was just saying,
It's an example.
that looks like real, what, like, that was the real distribution of the class, so it's like.
I never said that. I think the class is doing much better than this picture. So,
Let's hope in our grades.
sorry.
Let's hope in our grades on the board.
Yeah, that see that I can't. That would offend Uncle Sam. Yeah, it's about student privacy and everything. Yeah, just like we did height, I can't do sports. So the word I was looking for is bimodal, because simply that means there are 2 modes or 2 types of people who exist in this population. Okay, and generally when you think about the bell curve or the Gaussian distribution, you draw it like this. you have the mean, and then we calculate standard deviation, and then we talk about this being a mode or this being a peak in the distribution. Of course, I want to talk about this more quantitatively next lecture, but today I want to just discuss some examples. Okay, so can you give me some quantities which you approximated as following normal distribution, either in daily life or use in your experiments or in your other courses? Some quantities, yes.
Solar power output, like from solar panels, it's a really good one.
Okay, you need to explain further. Some quantities with justification. Because from those examples, I'm going to try and say what that distribution actually means. Yes.
Like gas consumption on your drive to work.
Gas consumption on the drive to work. All right. Can you tell me how you made that inference that it follows roughly a Gaussian distribution?
Most populations around the city are like really dense.
Okay.
And then as you move out, I would say the population kind of sprinkles.
Sure.
And so the general population would be going into the city to work. Then as they move farther away, they would be using more gas to drive.
Actually, if I ask you to name something for which either you have experienced it or you have data for, if I were you, what I would say is my drive to work is roughly 17 miles a day. Okay, I can factor in, assuming that my car is always in the same condition. Okay, there are some days in which the traffic is lighter or heavier. Some days in which I never stop at a red light. That does happen. I mean, I just catch a good break, okay, not the time. So there are some days in which I never just step on the clutch. All I do is just cruise and come here. So the gas consumption per day on some good days can be less, on some bad days can be more. And if I do this for several years, I have enough days or observations to say that my gallons per mile on a given day. If I take that quantity, gallons per mile on a given day, I can plot that. And let's say usually I use half a gallon. That's my average. And it could be 0.51, it could be 0.549. You can think about on both sides. Okay. If I take a large number of observations, anything more than 30, and try to do a binning, what it comes out to is a shape that looks like this. I remember it as, it just shows you like a middle finger. It's easy to remember these things if you have funny things to connect with. So you get this shape if you make enough number of observations. That's how I would justify your example. Any other examples? Yes.
Rolling dice.
Sorry?
Rolling dice.
Rolling dice. Okay.
Actually, no, that would just be equal on each. Never mind.
Actually, that is a good example for another topic.
Rolling,
Sorry? Yeah.
rolling weighted dice.
See, if you take number of gallons, it is a continuous variable. If you take height of 1,000 people, it is a continuous variable. You can have 5.8, and then you can have 5.8.5, 5.8.6, and so on. Dice on the example is fundamentally different because the number of outcomes are finite. A dice can only have 1, 2, 3, 4, 5, 6. If you have one dice, or if you have 2 dice, up to 12, 2 to 12. So that is fundamentally a different type of random variable, which we call discrete variable. And so far, all our examples, by consciously, I've been choosing continuous variables. We'll come to that next lecture. Okay.
Like calories eaten or whatever. Normally
You
about,
have to be more specific than whatever.
like how much you eat in a day essentially. Most of the time it'll be about the same, but some days you'll eat less, some days you'll eat more.
So you can take that sentence and generalize it for many things which you do every day. On some days, it will be a little higher, little lower. That generalization can be done. You wanted to say something?
Oh, no, it's not a text, it's not a play.
Number of, amount of time it takes.
Longer steps, but you can take it in the car and your plane.
Interesting example. So she is talking about wherever you park around campus, let's say, number of steps from your car to your desk or to your classroom. Is number of steps a continuous variable or a discrete thing? It's not continuous, but the statistics still follows a continuous distribution because how many steps does it usually take? You came up with the example, you have to say something.
Oh, let's say.
200? All right, let's take 200. Okay. Some days it is most days average is 200, some days it is 220, some days it's 192 in that variable. If you count steps, what is the resolution with which you can actually count? One. You can either count 1, next stop is 2, 3 in steps of +1. If you consider the value of the variable being around 200, 1 is insignificant compared to that average. So the distinction between discrete and continuous, if you think of your resolution with which you can collect the data. In this case, what is the resolution? 1. The resolution is 1. The nominal values are about 200. So 1 over 200 is a small number which you can almost treat like a continuous variable. If suppose I talk about the same example, but I talk about the number of steps from my office to this classroom, the number of steps is likely to be around 10 to 20, maybe 30, I don't exactly know. But in that case, the resolution becomes comparable to my nominal value. So it would not make sense for me to use discrete, but it would make perfect sense for you to use a continuous distribution. Does that make, do you see the difference? You talked about dice. There are only 6 outcomes. There are there is no other possibility. So you have to treat them separately. But when you take height, how many possible values can a height take, mathematically speaking? Infinite. Because it just depends on the resolution with which you can measure stuff. Number of steps is actually discrete, but for our purposes, it can be treated like a continuous variable.
In that kind of, could you do like distance traveled, based on like your path to get somewhere, and that could be a continuous thing, because you could always do more and more and more. It's like, instead of saying this he traveled like 500 feet and 12 inch and 13 inch or 5 inches, and then you could say like, I'm gonna look at even closer, and it turns out he did however many feet in like 5.6 inches, and yeah.
It's related to that in the sense, if I ask you what is the perimeter of a country, it's a classic example to talk about length scales. The perimeter of any country is technically infinite, because you could keep on splitting hairs. You can use a meter stick or a yardstick that is shorter and shorter, and your perimeter will keep on increasing. It will keep on increasing, but it will never zoom to infinity. But technically it could. It's kind of the same thing. You have to look at the quantity that you are handling. It could be a voltage, could be length, could be number of steps, it could be number of objects, it could be any number, it could be anything, but compared to the resolution with which you are measuring it, if it can be turned continuous, you use a Gaussian distribution. If it can be termed as a finite distribution, you use the student's t statistic or some other type of distribution. So next lecture, what is the time? Okay. So what I want to wrap up this unit on statistics is, I want to first introduce what is this Gaussian distribution. We'll do a couple of problems there, and then close off saying this. We saw Gaussian distribution students T distribution. These are not the only type of distribution. There are actually more distributions that you can remember. You are not going to learn all of them, but you should at least learn to look up all of them. So the book has an examples of a few distributions which we look up, and we are going to deal with only two. We dealt with one, the students T. We are going to deal with the Gaussian next level. Okay, but today's takeaway, I want you to remember this important step. What is binning? It is the act of classifying objects into categories defined based on some attribute. In our case, the attribute was height. In some other case, it could be voltage value, or it could be number of steps. It could be different things. But this process, if you remember, you get what is called the histogram, and the shape of the histogram, the kind of function you fit to the histogram data is what is called as the distribution. Okay, we'll see this with formulas next lecture. Okay. One last thing, I am kind of presenting this in a unconventional way for statistics. I'm not inclined on teaching you formulas or where they come from. I want you to think about this process, think about the numbers. The formulas, you can always look them up. But what I feel missing from most of you is you have no intuition about how these things are actually working. You are kind of doing the number crunching, but you don't have intuition. That's what I'm trying to fix. Okay. If you have any comments, please let me know, because in a way, this is also something I'm trying out to present. If it is not working, I need to hear from you. Maybe I can switch back to conventional way of teaching statistics. Okay, so please give me feedback. Thank you.